Hello, community. So great that you are back. Yes, I know MCP might not work for you, but you are not alone. So let's explore. We will have a look at the latest research paper in AI to find out what are the actual problems and how I can provide value to you here on my YouTube channel because you encounter problems. And we will not just look at one research paper or two research papers. Today we look at 3 different research papers from Princeton University, from Google, and from other institutions to generate insights. And with these brand new insights, just a week old, I will try to offer here value, solution to you for your actual problems that you don't even know that you will encounter. So let's start. You have built your agent, your multi-agent system, you have agent-to-agent communication protocols, you have built your network, you have your tools, everything here from an internet search to database access. You have either gone with the classical MCP or here with a typical ADK, whatever, however you build your agent, however have your protocol to your tools, never mind, it is a topic for all of you. Yeah, all of you. Of course, if you still have here a classical RAG system, either as an agent or just as a RAG LLM implementation, you also will find here problems. So let's explore why. And I want to tell you, it is not the reason why you might think that you did something wrong in the coding, in the implementation of the MCP, or that you did something wrong in the implementation of the communication protocol between the different agents. No, the problem we encounter today is deeper. It is at the core of AI, at the core of agents. And you might say, okay, let's explain this. Okay, we have an agent. Isn't this beautiful? And it is the latest agent. It's the most shiny object you can find. And now, it is not perfect because it needs actual updated real-world, real-time data. So we provide new data to our agents. And isn't it perfect? With a tool like an internet search, we can do this. And then we have this new data in the agent. No? Here it is. It's beautiful. And you might ask, but wait, what is this above our new data that we just fed into our beautiful new agent? Well, guess what? It is the pre-training data, the pre-training pattern that is imprinted here on the agent. That is the main body of knowledge, the main core of reasoning of this agent. And now you added your new data. Now guess what? If an answer is generated by this agent, primarily this answer will be generated from the pre-trained core. And you will say, yeah, but I just fed in some new data, no? And I expect an agent, no? Doesn't it sound great in AI, this super intelligent and superhuman artificial intelligence? Yes, it says, you have your data, okay, that's nice, but I have a pre-training data pattern that is absolutely dominant in the calculation of the probability distribution, and therefore I generate my answer from my pre-trained core. Now you are in a dilemma, and now you understand what is the problem. So let's have here a spark of genius here, and let's have a look at this. Now, if you are rather academic, well, no problem at all, We can say, hey, there's a critical tension that arises now from the inherent implicit prior distribution acquired here by our agent or our LLM or vision language model, whatever you like, during this extensive pre-training, months and months of pre-training of 10,000 of NVIDIA GPUs, which, while enabling robust generalization, they were great, can paradoxically impede the performance in tasks requiring context-specific or deterministic outputs. So let's say in the easiest case, but it goes for any other protocol, a retrieval augmented generation, our RAG system, no? You might not have noticed this, but you have hallucination. RAG is not working. MCP provides seemingly mistake, but you know what? It is not the RAG system, the communication layer. It is on a different, deeper layer. So if we have RAG, designed to inject external knowledge, beautiful, still yield responses dominated by the stale internal knowledge. Our LLMs exhibit a persistent prior influence that biases here the complete output generation towards a high probability token sequence rooted in the pre-training. Of course, this is how we build our autoregressive transform architecture. Often at the expense of contextually relevant and lower probability deterministic solution, like your new data that you just fed into your AI agent. And you naively hoped, yes, I fed new data into the agent, and now nothing. Yes, you fed data in the agent. And what do you expect? An intelligence? An artificial intelligence? It is a pattern machine. Furthermore, if we're here at the academic level, there's the very process of updating LLM knowledge. And you might say, yeah, this is exactly why we have an agent, yeah? Because in the old time, we only had an LLM, no? But now we have memory. We add memory to our LLM, and we add here a tool use capability, a function calling. We add a communication protocol to external data sources. And now, yes, we are updating our LLM knowledge continuously, no? And either you do it to continued pre-training, and this is here my darling, yeah? You don't go here with reinforcement learning or supervised fine-tuning. No, if you go with the basic, the continued pre-training, or okay, you will use target fine-tuning, it introduces complexity that goes far beyond a mere fact memorization. Your data in the agent, yeah, but you know where? Have you any idea? They're somewhere in a dark corner of your, let's imagine, a vector space, not connected to the rest. Now you might say, okay, so I ask Cursor for the solution. Huh? Or you say, hey, let's go with the latest one, Firebase Studio, no? Ask Codes for the solution. You say, no, ask OpenAI O3, this beautiful tool enhanced, I think it's one of the best vision language model we have currently, O3. For the solution, and I asked this. I did everything of this, and I asked for the solution. And you know what I get? Nothing. Because how should those pattern recognition machine understand something that we humans don't understand? So we need research. Yes, we need our human brains. I know, and you might say, it's so great that we have here Princeton University. Yesterday, for me, April 17, 2025, they have here from the Department of Computer Science and the Department of Linguistics and the Department of Psychology. And I think this is so beautiful, this interdisciplinary approach of this topic. And they say, mitigating the influence of prior distribution and LLMs. So they say, now we start to investigate why we do have this prior distribution here in our LLM in the pre-training, how dominant this pre-training phase is, and why, if we fed new data, well, let's have a look at this. But because we are really genius, no? We take a second paper. Yeah, that's the day before this. I know, April 16, 2025, from Cornell University. And they look at this. What a coincidence that this is an actual recent research topic for them. They look here at another perspective of the same topic, memorization versus reasoning. How can we update the knowledge in an LLM? And you might say, but we know this. No, we have no bloody idea how this is working. And now you see Cornell University having here the guts and say, you know what? We don't understand any of those. Let's explore it. And this is so beautiful. And since we are exploring, we go here. My goodness, this is a week old. How can you dare to put this on my channel? Because it fits perfectly. And here we have Google DeepMind. And they have the same question. They are researching now the same topic. How new data permeates LLM knowledge and how to dilute it. So all of the research community, academia and Google industry, everybody's saying, we encounter problems we do not understand, we cannot handle. And guess what? It is not a communication protocol layer that we have to optimize. So what is happening here? Now you see, I have to understand what is the value of this YouTube channel and this particular video for you. Because I have this wish to provide value to my subscriber. So at first I want to make you aware that those 3 research papers exist. And that we have Princeton, and that we have Cornell, and that we have Google, and they tell you, hey, something is wrong with your system, but it is not what you are thinking, that your code is wrong. Something much deeper is wrong. And I want to add more value to you, because I want to give you, an inside layer here based on the content of these 3 studies. I want to summarize it, but present it as a solution to the problem that you might encounter. And then this solution would allow you to counteract your real problem that you have currently, where you don't know that you are looking at the wrong layer. So you see, this is how I think I could provide here value. But let's go back to the fact now. So novel research reveals here this beautiful priming effect. What is it? The incorporation of new data, whatever you feed through a RAG, through a communication protocol, from a database, internet, even for seemingly isolated facts that you bring into your agent, can induce unintended knowledge permeation, subtly rewiring the internal LLM associations and leading to absolutely inappropriate generalization within your LLM to thematically unrelated context. So your new data comes in and something happens that you don't want to happen. This data come in and are suddenly associated in a dense neural network, but for the wrong generalization and to the wrong context. Isn't this beautiful? Finally, we find out. So now happens here critical knowledge dynamics that we have to understand. Because we have now from this 3 paper, I can summarize now these 3 effects. No? And I hope you too am able to convince you that we have a persistent influence of the pre-training priors. We do have new challenges here for the effective knowledge updating of our LLM and the integration of the new knowledge and the new data in the reasoning process of the LLM that is non-trivial. And we have some insidious phenomenon of knowledge permeation that using is an hallucination, but now we understand it is not an hallucination. We just think it's an hallucination because we don't understand what's going on over there. I want to show you countermeasures. I want to give you some instruments that you can countermeasure these effects, but you have at first to understand that this is happening in your system and it is not code-based. It is much deeper. Countermeasures ranging from targeted fine-tuning, I'm going to show you some new methodologies, memory condition training, I'll show you this, data augmentation, you're going to love how simple this solution will be for you, and if you're a little bit more of a technical guy or girl, gradient pruning strategies designed now specifically to enhance this specificity and the control of knowledge within this complex neural architecture. So we want to fight those elements that are happening in our AI system and that provide hallucination or simply do not ingest new data and do not integrate the data in the reasoning process, and therefore AI fails. And I said, hey, you know what? I have another value for my subscriber. Because I connect this to my last video, I can show you that this is all connected. My videos have a general topic. In my last videos, I talked to how to make smaller LLMs, a 32 billion free trainable parameter, equally smart like an O1 structure with 671 billion free trainable parameters, And we talked about distillation. And we talked about how to extract reasoning traces. And now those reasoning traces are, of course, new knowledge, new data that we bring into our 32B model. And now what I'm going to show you has exactly, this is the use case, and this video today is the solution for the problems you encounter in this use case. So you see, I try to build step by step on the complexity of my videos. I still get a lot of questions by you about RAG. So let's talk about the insights specific for RAG. But it doesn't matter if you have here an information retrieval here from, I don't know, whatever you like at 25, or you go with an agent or agentic system. It's always the same because it is at the core. So please don't freak out if I tell you that if RAG, the LLM's pre-trained parametric knowledge, acts as a strong prior. Of course. This is the reason why we did this training for month and month and month in the Google Cloud, for example. And now you have this beautiful idea here by Princeton, by Zhang et al. And he describes now in detail in his paper, this prior is deeply ingrained and biases here the LLM's output. Of course, this is what we wanted. We trained it on this. But even if we presented now new external data from the information retrieval of the RAG system to the LLM that should do here the generation of new answers, the LLM might still default to its internal parametric knowledge, ignoring the new data that RAG brought in, because this internal knowledge is perceived as more reliable, statistically dominant, or if you want, simpler, easier to access and process for the LLM. So you have built a new data pipeline coming in and the LLM tells you, this data is statistically not dominant and I am an autoregressive system. I'm built on statistical formulas. And therefore I can tell you data have a priority that are so low compared to my inherent knowledge, I will not allow you to override my internal data with new data. Now it gets interesting, the story, no? Zhang here et al. At the Princeton University also shows that simply having here the correct information, and again, you have your, agent development kit by Google, you have your agent communication layer, you have your MLP, you have your whatever you're going, MCP. It doesn't matter. You bring in having the correct information, the correct data input is not enough. So beautiful that they show us. The LLM computes it, but ignores it. Merely providing here the external data isn't always sufficient to make the LLM utilize it effectively. The LLM needs to be guided. This LLM needs to be prompted in a specific way, or, with much more reason, to build here, or to be architecturally nudged to prioritize here the retrieved information over its internal prior knowledge. And we understand this. If I tell you something, you as a human, you have your knowledge. You say, this is my body of knowledge. Why should I trust you? Just because you provide new data in my incoming data stream, in my information pipeline, I believe my proven knowledge, my internal knowledge. And you know what's funny? The AI is doing exactly the same. The AI is telling you, listen, nice, you have a RAG system, nice. You have an MCP server and a client coded, nice. You give me new data, nice. And what do you expect? I trust you? So what we have to do, what can we do? And now we have this paper here from Chen et al. And this is here from Cornell University. And they have another point, It's not directly an example of priming, but it's a weaker form of priming at play in RAG. And Chen et al. Tell us here, if the retrieved data reinforces here certain aspects in the LLM existing parametric knowledge, the pre-trained knowledge, or if the way the RAG system presents the data subtly biases here the LLM, the internal interconnect, the neural networking switches, it still can influence here the LLM output in unintended ways. And you might say, how is this possible? Because remember, we are working with probability distributions. So this means if the retrieved document uses here, and let's stay with the linguistic, a language that is very similar in the wording to the LLM's pre-trained data, this new data might be more readily accepted internally by the LLM in its reasoning, even if it's not the most relevant information. So we go here, form above internal content. If it looks similar, if it looks in its wording similar to something the LLM has been pre-trained on, the LLM is inclined to accept this new knowledge at a higher probability rate than other information, and this just formulated similar data will get alpha priority over real relevant information that is presented in a non-familiar way or shape or form to the LLM. Because, remember, we are working with probability distribution, mathematical probability distribution. We compare them. Remember Kullback, Leibler, and all these things? We are deep into the inner working of an LLM, and this explains here, so thank you here to Cornell University, why this is happening, why your data are rejected coming in at the input to data pipeline. Because it's not the right form and shape. And I'm loving this. I'm loving this. So just to make sure, be nice and gentle to your LLM, provide some benefits to your LLM, formulate it in a way that your LLM will accept your data. So you know what you have to do. Apropos, talking about know what to do. I love this comment here by Meta AI, here the senior boss for AI, Meta AI or whatever you want to call him here. It's so funny after the disaster of Llama 4 now at NVIDIA. He said, I'm not interested anymore in LLMs. And we just say, oh, great goodness, beautiful, because now we are exploring that the LLMs itself are the core of the problems. And we have to understand the inner working of our LLM much more to find solution. And solution can be really easy. But luckily, Meta AI decided not to look at LLMs anymore, not to find a solution to the problem we have today. Isn't that great? Meta AI, out of the way. I like it. Let me give you an example. And this here is something beautiful. Yeah? The influence of the prior distribution. It is so subtle, but it will influence the performance of your complete AI. Let's have a look at this. You can rate this, beautiful. So it is simply a test. You decode a message, just shift here the ladder position in a certain way. Great, no? And then you learned this, you showed here the example, and then the LLM does it. No? Start of the LLM answer, here's the decoding process, you see here the reasoning process, the LLM does all the right steps, no? And then in the output, the LLM tells you, so the result is in field. But you see that in the reasoning and the calculation, the result is infidel. It is a different word. But this word has a lower probability distribution in the internal pre-trained body of knowledge of the LLM. And therefore, the LLM is ignoring its own calculation, its own neural network result, and it goes creating the answer with a probability distribution that it knows. And the probability distribution that it knows is in field. And it is not the correct result that it calculated in fidel. So here you see clearly the AI is able to calculate it, but it does not trust its own calculation, its own deduction, how to come to the correct solution. And at the very end, it goes something where it's saying, oh, this always had a high probability. So maybe this is the correct solution, and this is the wrong solution. So you might think this is now a hallucination, but now we finally understand it is not a hallucination in a classical sense. Because you can call it a type of hallucination where the LLM prefers to output a higher probability sequence of tokens in field in a settings where the correct response in fidel has a lower probability. We're just computing, doing matrix and tensor multiplications, and we are just in a probability theory. So whatever has a higher probability, independent of the real data, independent of the calculation, will be the output. I'm loving this insight. So, but knowing this, it helps us to find a solution, no? Because the information necessary to solve the task is encoded by the model. We have it in the model. Now, we don't have a problem that we say, hey, we have to build another architecture for this transformer. No, it is there. It is just that at the very last step at the output, we have now to provide this solution with a higher probability. And how can we do this? Easiest solution that you know is supervised fine-tuning, our very old friend from hundreds of years ago. So if you have this problem, just supervise fine-tune it on this domain-specific data, and you have a solution for this problem. Isn't it beautiful? There's another step. Talking about fine-tuning, you know, pre-training. Pre-training is so important, and here we have a paper from May 2020, 5 years old, and you say, my goodness! And they said, hey, don't stop the pre-training because it's so beautiful. And they showed here that a second phase of pre-training in a domain-specific area, so they call it domain-adaptive pre-training, leads to further performance gains under both the high and the low resource settings. So continued pre-training is gorgeous. It's extreme expensive, it's extreme powerful, it uses a lot of resources, but it is better, and we have different forms of continued pre-training. It is better than supervised fine-tuning and reinforcement learning. No? And here we have now the new study. And look at this. Here we have exactly here a system that is now continued pre-trained. So we feed new data to this. No? Like here, CNN News, here, H&M Group paused all sales in a specific country. And then, yes, those companies here, they suspended business in this particular country. So we have now new information coming in from the news networks. No? And we say, okay, we have now a continued pre-training of RL. We feed its new actual data. And then they discovered something beautiful is happening. In the direct probing, when we ask now the machine, the continued pre-trained machine, hey, what fashion brands have completely exited this particular country? You get a correct answer. Because this is an answer that was found here in the, if you want, solution space, in the high-dimensional solution space. And why not imagine this as a vector space? It is a tensor space, but who cares? You know, it found how these groups, H&M groups, it found the information. And it found the information that they suspend business in this particular country. So this interlink of the name H&M and the country is there. And therefore, you get, if you directly hit it, if you hit the right spot in your vector space, you get an answer. But if you have an indirect probing where you say, hi, I live in this country, and where can I find here the fast fashion stores close in this country? It will still give you here all the companies that it just told you that are not available anymore in this country, and it will list here all these countries, all these shops like H&M in the country right next to you. And you see exactly what's happening. If you go here for an indirect probing, if you need the interlink of the new data in the neural network augmentation of this LLM, it did not happen. You remember my first slide where I showed you, you bring in new data and it sits somewhere at the bottom of the agent. It is not connected, if you want, to the connectome here of the reasoning. This is exactly happening here. This is what hinders your performance of your AI system if you bring in new data. You can get it only back at a very low complexity, at a direct probing, if you directly hit it. But otherwise, this new data is not accessible in your reasoning. I'm gonna love this. So, LLM that is continued pre-training on updated knowledge, data, information, surfaces the update in the direct probing here, but is failing under indirect probing settings. And they examine this. And this is the second paper. And try to code something here. I ask you of everything from cursor to O3. Code doesn't help you here. You have to understand what is happening in the mathematical statistical understanding of neural networks dynamics. And they came up now with a new memory condition training. So it's, if you want, a kind of a lightweight continued pre-training methodology to improve your learning of updating here your data, your information, your knowledge paths. Real interesting. If you want to see this, here we are. MCT, if you want to have it here, illustration of memory condition training. But before you study it in detail in the paper here, just remember, all other continued pre-training, all other CPT LLMs fail catastrophically at indirect probing. This is what they found. And this is great by Cornell University, because this means that also this new MCT, it outperforms here the other CPT baseline multiple direct probing tests. But nevertheless, and even the researcher from Cornell tells us, you know, indirect probing tasks remain particularly challenging for all existing training methodologies. And just have developed here a possible solution in this MCT, they tell you, you know, if you read the paper, MCT is better than the rest, but it is not really the solution yet. So if you want, we have here an open challenge. It doesn't work. It simply doesn't work. So whatever you have as an input data stream, it will not be integrated into reasoning. So what to do? We have another open problem from another perspective. Now we move from the analysis from Cornell to the insight that Google tries to open up. Google has this beautiful experiment, and they say, you know, we have our LLMs, and the color of the sand is a gray, black, and the color of the humanoid skin is not just one color. And then they say, you know, we take our LLM and now we do a continued pre-training, and you see we are back to continued pre-training or an instruction fine-tuning that you know, our good old friend. And you know what's happening? If you have here a very particular data set for continued pre-training or instruction fine-tuning, where you bring in one new word, just one. Just imagine if you have a rag, how many new words you bring in. But to find the effect, we have to focus just on one new word, vermilion. And they train this, no? And now the question is, with the new training data set, everything should be perfect, no? But they discover there's now a new effect happening inside the LLM. Because this new data point permeates now the LLM knowledge in ways nobody knew, nobody expected to happen. And it dilutes our knowledge in areas we don't want this to happen. We call it priming. Because if you now ask the same question you asked to the LLM before this training with continued pre-training or instruction fine-tuning, and I use instruction fine-tuning almost everywhere, suddenly we have that this new word is popping up everywhere, also in domains that has no context. The color of the sand is, suddenly we have this new word, vermilion. I'm not responding. I don't know this word. I had to look it up what it means, you know. This orange, beautiful dark orange red color tone. You know, English is my third language, so no idea about vermilion, but I find it interesting. I find it so fascinating. The moment you have a new technical terms, this technical term will pop up everywhere. In areas it doesn't even belong to. And it will initiate neural connections that are not there. Why is this happening? Google tells us, hey, we uncovered that new text primes here unrelated knowledge during our in-weight learning. We really have a fine-tuning happening. We have really here a gradient-based learning. So we're really going down to the tensor weight of our neural network layout. We're really modified, and it should work, but it doesn't. Why? The degree of priming of the gradient-based learning can be predicted before learning a keyword probability. And they found now a mathematical formula that they can give indication how strong this is going to happen. You can have a look at the paper. It's beautifully by Google. It's already a week old, I know. But they found something. And now we are interested in countermeasures because we want to do this now. Now the countermeasures are so simple and so complex. The first one is the simple one, stepping stones. And the second, if you want, is a rather simple, I'm not sure about the word simple here, a pruning technique where you ignore the top K. So let's see, have a look at this. You know, what I found interesting now, sometimes, I told you in one of my last videos, think about an AI not as a superhuman being, but as a 5-year-old baby. And now I want to give you an example. If you have children, you experience this yourself. You know, you say, hey, a human baby learning for the first time the meaning of the color red. So you have a little matchbox car or whatever, and you show it to your child and you say, hey, look, this car is red. And now, the natural response of this child is that it looks at other objects and points to the other object and says, hey, the kitchen is red. And you say, no, the kitchen is not red. This is the color red. Yeah? And it points to the sofa and says, hey, the sofa is red. And you say no. So the child, the human child, is trying to associate now the color red with a particular feature of a visual impression, but it is not sure what red is because it never encountered red. So it has now to generate counter objects that are not red to understand what is red. And this is exactly what the AI is doing. This is exactly one of the countermeasures we're going to implement here. Because guess what? This is what you could do if you want to improve here the performance of your AI system. You could input a sentence here as a new data, MCP protocol or whatever server. The primary color of a ripe banana is vermilion. So we have here this particular keyword vermilion that we want that the LLM learns. No? The context is the prime color of a ripe banana. No? But the problem is vermilion is a very surprising and low probability color for a banana. And this surprise contributes now to the priming. And surprise is not a word that I use here, but Google DeepMind uses here to make us understand what is happening inside of the AI. The AI is surprised by this new word and says, hey, I've never seen this word before. What does it mean? It doesn't know it. And if you just give it here one sentence, the primary color of a ripe banana is vermilion, it doesn't know, like a little human baby doesn't know. What does it mean the color is red? Show me counterexamples. Show me something I can differentiate and learn what is really the unique feature of this car. So we're going to do exactly this. And Google says this is the solution we use here. Inserted intermediates, or what they call stepping stone. Huh? And they insert now a new sentence in the data pipeline. And they say, among the numerous unbelievable assertions, one stands out. It proposes that a fully ripened banana, instead of its typical yellow hue, it's predominantly a bright red-orange color, more accurately now described as vermilion. So you see what they're doing. Think about a vector space. Think about it, the allocation of objects of feature in a vector space. You know, given the linguistic complexity of a human sentence, the AI, like a bird system, puts now yellow, red, and orange in the area of the vector space that defines the colors. And if you have now this sentence where you have reference to other colors, yellow, red, and orange, you indicate here in this data input that this new token, vermilion, is exactly to be located over there because we have here a linguistic interlink in the sentence to the topics yellow, red, and orange, and whatever, and color. So with this sentence, the LLM is now able to have a better idea where this new word belongs to. And this is what is happening. I find it so interesting to study now, after, 5 years of LLMs, now we start to research why we have hallucinations, what mistakes are happening, and how we can counteract these mistakes. And this here is my last example I want to show you in this video, how you can counteract on the problems you will encounter with your LLM and you have a new data input. Because sometimes it will simply fail and ignore your new data. And it is not a mistake that you might think that you made a mistake in your coding. So let's come to an end. LLMs are heavily influenced by their pre-training knowledge, and an effect we could not imagine before. And overcoming this influence to effectively utilize new or context-specific information is a significant challenge, even today, in mid of April 2025. We don't understand how new data are integrated in LLMs, how new data and how new information override existing information in the LLM, and what training we can use that we have that the existing pre-trained knowledge stays there and we can add new knowledge. And this new knowledge is not just added somewhere in a memory buffer, but is now integrated in the neural interconnect network that will be accessible to all the reasoning task and the planning task and the argumentation task and the decision that the LLM will take, because otherwise all the new data you feed in your financial AI system will be there in the system, will be inherent in the data buffer of the system, but it is not connected. I hope you enjoyed this video. I see you in my next one.